really. Okay, derivatives of exponential functions. So a function of the form f of x equals b to the x, right? So the variable is in the exponent. So from first principles, we know that the derivative is defined as I need some space in there. The limit, we know that it's defined as the limit as h approaches 0 of f of x plus h minus f of x over h. So if this is our function, then this will be equal to the limit as h approaches 0 of b to the x plus h minus b to the x over h. And we note that we've got a b to the x as a common factor there, right? Well, we could split this out, I guess, right? We'll say that it's whoops. So, you know, how do you add exponents? You multiply powers with the same base, so I'm going to split that out. So it becomes a little more obvious that, hey, I can factor out a b to the x, right? Because it's common to those two terms. So let's pop up here. And that gives me b to the h. Look more like an h. B to the h. Not very, getting very good h's. So its limit as h approaches 0, b to the x times b to the h minus 1 over h. So the b to the x term, really nothing's going to affect that, right? Limit as h approaches 0, that's not done with respect to h. It's really just a constant, okay? Which means that we can just move that out in front of the limit, right? So we can say it's b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Now, you may not remember this, but we've seen that limit before. A long time ago. Well, it can't be that long ago. We didn't start all that long ago. But we have seen that limit before. So let's go look at this a little bit, right? Let's just look at this. And let's try it with a couple of numbers, right? We'll throw in a number for b. Let's try 2 and see what we get. So I want 2 to the h minus 1. Now I'm going to use decimals, so I'll do it as an x. So 2 to the x minus 1 divided by x. Right, and we can see that we've got a value here of, as we approach 0, whoops, I mean 0 is, what? So we're approaching about like 2/3, right? 0.67, undefined. And let's do the same thing. Let's just copy this. Let's copy this and paste it. And we'll try that with a 3. And with 3, we can see, so with 2, we can see we're a little bit under 1, and with 3, we're a little bit, oops, over, not getting a big trace here. So 1 point something-ish and 0.67. Well, what would be nice is if we could find a value of b so that this expression here were equal to 1. So, towards that end, I should go back there. I have this set up so that I can't actually use it. I have this set up with a slider for b, right? So what we want to look at is say, hey, when do we get to 1 here, right? So, I mean, we know what happens at 2 or 3, right? Like there's 3 and we're a little bit above. And there we are, we're about on 1, right? 2.7, and we're getting close, right? Close to 1. And if you remember back, or if you check back in your notes, you remember that's the definition of the number e, right? So e is defined as the limit as h approaches 0, e to the h minus 1 over h is equal to 1. Okay? Look back in your limits notes and look up the definition of e, and you'll see that, right? So, well, first of all, okay, remember what this is, right? This is f prime of x. That's f prime of x. This thing here, the limit as h approaches 0 of that, that's really like f prime of 0, right? That's the slope at 0. So we've got f prime at x is equal to b to the x times f prime at 0. And then the idea is, hey, if we could get this to be 1, then the derivative will just be this, right? And where does that happen? That is 1 when the base is e. Okay, so remember back. So back to notes on limits. Where e is equal to the limit as h approaches 0 hang on. When that's equal to 1, right, sorry, there we go. The limit as h approaches 0 of e to the h minus 1 over h is equal to 1. Okay, so we want to use e as the base of the logarithm, right? And that gives us this. It says if f of x is equal to e to the x, then f prime of x is equal to e to the x. Right? So in other words, the slope of the tangent line is equal to the y value of the curve e to the x at that point x. Right? This should be a special, it's like Pi Day, right? There should be a day to celebrate the fact that there's a function whose derivative is just the function itself, right? That the derivative of this function is the function. Okay? So the derivative of e to the x is e to the x. Or, expressed in Leibniz notation, d by dx of e to the x is e to the x. And so let's do 162 examples. We'll do a number of examples and then turn you loose on it. Does any of your assignment have an e in there or no? No, okay. Then you'll have to wait till like Wednesday, I think, before you get the last key to do number 7. Yeah, which won't take long once you've got that key, right? So it's not, hopefully everything else is done. Okay, so f of x is equal to e to the x minus x. What's f prime of x? And so that's pretty easy, right? That's just a sum or a difference. We'll go back to the sum and the difference, right? So f prime at x. So the derivative with respect to x of e to the x minus the derivative with respect to x of x. This we just defined is e to the x, and that's a 1. So it's just e to the x minus 1. And then let's say we do determine f prime. Let's do f double prime. So that's f prime, first derivative. And then the second derivative. So f double prime of x is simply e to the x. Okay? Derivative with respect to x of e to the x minus the derivative with respect to x of 1, which is e to the x minus 0, right? Or just e to the x. chance. Put that down. I don't rush it. I'm going too fast. Let me know. Okay, slow down. It's like that stuff calculus students never say. Could you do that example faster? Could you skip some steps? Yes. That's right. Okay, so let's find, got this definition, we're going to use product rule here. So we kind of cover old ground, right? Sum and difference rule, product rule, we'll throw in a little quotient rule, some chain rule, and some implicit differentiation. But we've covered everything that we know how to do, or should know how to do by next Monday, right? So if f of x is equal to x times e to the x, determine f prime of x and the nth derivative of x, right? Which basically means we're probably going to do the first derivative, second, third, kind of see if we can find a pattern going on there, right? To get the nth derivative. Okay, so f prime of x. So using the product rule, it is the first thing, right? So x times, now do you want detail or not so much detail? Like I can write d by dx of e to the x.
We know that.
Okay, you know that's right. It's the product rule. Come on, we've been doing that for weeks now. Or days anyway. Okay, what's the derivative of e to the x? E to the x. Plus the derivative of the first term, which is 1 times the second term, right? So it's plus 1 times e to the x. Well, we got e to the x bracket x plus 1. Let's clean that up. Okay, so let's do the second derivative. Now, we've got two choices, right? We can either do it as a product or we can do it as a sum. Right, well, let's do it as a product. So we've got e to the x times x plus 1, so it's e to the x times the derivative of this, which is 1, plus x plus 1 times the derivative of e to the x, which is e to the x. Which gives me, well, I got another e to the x, right? So let's move that up there. So that's e to the x times x plus 2, right? Because there's two. So we got, if you expand this, you're going to get e to the x plus x, e to the x plus e to the x, which is 2e to the x plus, right, and that's where that x plus 2 comes from, right? Because we've got 2 e to the x's, right? You've got the 1 here, and then when you distribute this in, you got the x e to the x, and then you've got another 1 here, so that's why there's 2 of them. So what do you think the third derivative is going to be? What's the fourth derivative? So what's the nth derivative? And there's your nth derivative, right? Now, you know, if you're not certain that it's an x plus 3, then you could certainly do the third derivative more explicitly, like actually write it out and then convince yourself that yes, it really is. There are 3 of them, and then, okay. But you can kind of see what's going to happen. It'll be this, then it'll be x plus 2 times e to the x, and then it'll be, you know, so e to the x times 1 plus, and then there'll be 2 of them. That'll give you 3 of them, and then so on. Okay, so there you go. Kind of neat. Over, it says. Ah, quotient rule. Yes. All right, what have we done? Sums, products, quotients. Find the equation of the tangent to the curve, e to the x over 1 plus x squared, at the point 1, comma, 1/2 e. Right? So the x value is 1 and the y value is 1/2 e. So what are we really looking for, right? We're looking for y prime at 1. Right? That's what we're looking for. Okay, so we need y prime at 1. Y prime is the equation of the tangent, right? And we want it at that point, so we need y prime at 1. Okay, so y prime equals. So quotient, right? You go with quotient, you know, how much detail do we want to see? It's the numerator, it's the denominator, times the derivative of the numerator, which is e to the x, minus, so remember that's what you're looking at, right? Like when you see an expansion of a quotient, then you're saying, I should see the numerator times the derivative of the denominator, or should see the denominator times the derivative of the numerator, which means e to the x must be the derivative of the numerator, minus the numerator times the derivative of the denominator, which is 2x, over the denominator squared, right? So you'll notice we have a little thing in common there, which is e to the x. So let's go across. Okay, what have I got? 1 plus x squared minus 2x over 1 plus x squared squared. So let's clean that up a titch. So we've got e to the x, let's go 1 minus 2x plus x squared over 1 plus x squared squared. Now you could kind of stop there, right? I mean, just throw 1 in for x and then evaluate it, but this could be cleaned up a little. That actually factors, right? So 1 minus 2x plus x squared is 1 minus x quantity squared. Right? We get a 1, we get a minus x, and another minus x, which is your minus 2x, and you're squaring the x, getting plus x squared. Okay, and we want y prime at 1, right? So it's e to the 1, 1 minus 1 squared over 1 plus 1 squared squared, which is 0, because 1 minus 1 squared is 0, and the numerator becomes 0, and the denominator is who cares, but not 0, but I care that it's not 0, but it's not 0. So then it's just 0. Okay, if you get 0 over 0, then you know you got to deal with other things. But. So it's 0. Which means the tangent is horizontal at that point, right? So if we graphed that and looked for when x was 1, we would expect to see, you know, something like this or like this, because we would have a horizontal tangent, which if you're watching on video makes no sense, right? I mean, but, so you would expect to see something like this or like this at that point, right? Which would give you a horizontal tangent line, you know, which tells us lots of stuff that we'll get to know in the next unit. Right, so you go back to 20-1 and say, why didn't you teach us this then? Okay, so everybody got that down? One more, I think. Two more.
So you don't have to, like...
1, 2, 3, 4 more. 4 more. I have 4 more.
Yeah. If you were writing out the equation of the tangent line, it would just be like y is equal to 1/2 e, right?
Find the equation of the tangent to the curve at that point. So it's y equals 0.
Okay, so you don't have to write out the equation.
That is the equation. The equation of tangent line is y equals 0. It's flat, right? You know, if the equation of the tangent line was y equals 2x, then we would have a line going like this, right? At that point. This is just y equals 0.
Yeah, I know, I'm saying you don't have to write out the equation.
That is the equation of a line. Yeah, y equals 0. We can't write it in the form ax plus by plus c equals 0. It's the equation of the tangent at the point 1, 1/2. Right? Yeah.
The slope of the tangent. Yeah. The slope 0. Yeah, the slope.
Well, the slope is 0. You got y equals 0x plus. It's just y equals 0x. 0.
Yeah. No, it'd be y equals 1/2 e. Yeah. That's what I'm saying.
Oh, yeah. Sorry.
Okay, so I wasn't.
So y.
Yeah, I was like.
Gotcha.
No, it's x minus 1.
So there's our slope, which is 0, and there's our b value. So then what would we get? 2y is equal to e. So 2y minus e equals 0, right? Sorry, my apologies. You're right. You're correct. Should have said the slope then. Yeah, you're right. Should have graphed it. Yeah. So it's just a flat line passing through 1/2. It's horizontal coordinates. Good. Okay, a few more. So what do we need? Chain rule. We need to do the chain rule. And let's throw a little trig in there while we're at it. Okay, so remember, you will have formula sheets for the test, right? But what's on that sheet is what you get. Okay, nothing else. Okay, so this is the derivative of the outer function, okay, which is e to the sine x. The inner function is sine x, right? So derivative of the outer function with respect to sine x, which is e to the sine x, times the derivative of the inner function, which is sine x, and the derivative of that is cos x, and that's it.
We're supposed to sit on that bench. Wait, how did you do cos x one? Sorry?
The derivative of sine x. So it's the derivative of the outer function, which is e to the sine x, right, with respect to sine x, and the derivative of that is just e to the sine x, times the derivative of the inner function, which is sine x, and the derivative of sine x is cos x. So let's take that up a notch. Let's do e to the secant 3 theta. Okay. So when you see e to the anything and you're doing your derivative, you just start off with it's the e to the anything, right? It's the e to whatever it was. So this starts off as e secant 3 theta, right? It's the derivative of e secant 3 theta with respect to secant 3 theta, which is e secant 3 theta times, okay, now we need the derivative of secant 3 theta, right? Which itself is then going to invoke the chain law, right? Chain rule, not chain law. So the derivative of secant x is sec x tan x, right? So it's times sec, now in this case, x is 3 theta. Okay? So now we're doing secant 3 theta. The outer function is secant, the inner function is 3 theta. So the derivative of the outer function is sec 3 theta tan 3 theta. The derivative of the inner function is 3. Okay, so multiple applications of the chain rule. Right? And so let's just move the 3 up front. So we'll get 3e to the secant 3 theta times secant 3 theta tan 3 theta. Okay, so when you see e to the anything, first thing you write down is e to the anything. Like just, it is what it is. That's that derivative, and then we need to apply the chain rule with respect to whatever's up there, right? And find its derivative. So with sine, then it became cos. Okay, y equals x times e to the negative kx. So we have a product, right? We've got x times something, and then we've got an e to something negative kx, so there's chain rule there, right? So product says we take the x times the derivative of e to the negative kx, which is e to the negative kx, times the derivative of negative kx, which is negative k. Okay, so there's the x, that just comes from here, and then this is the derivative of that, right? Plus, now we take the e to the negative kx times the derivative of x, which is just 1, right? Okay, so it's the first expression times the derivative of the second expression plus the second expression times the derivative of the first. Okay, and then we simplify. So we're going to kind of obviously end up with an e to the negative kx as a common factor. Right? You know, we're going to end up with e to the something as a common factor whenever we do a derivative with respect to e. Okay, and what do we got here? So here we've got negative kx, and here we've got 1. So it's e to the negative kx times negative kx plus 1, or so one of the big things on a test, as always, right, is when you're doing multiple choice, you get an answer and you look and it's not there, then your question is, well, do I have, you know, I've got negative kx plus 1, they wrote 1 minus kx, same thing, okay? So on a test, you're always looking, especially, you know, you don't find the answer, don't panic, right? So on the Hitchhiker's Guide to the Galaxy, it says, don't panic. So don't panic, just look and say, okay, do I have some variation? Is there something I can do? You know, I'm looking at this, but they're showing a factored form of something. I need to factor this out, and what do I get? There we go. All right, let's make things even more fun. Okay, so E is sine squared. I'm just throwing like hard ones at you now, right? I mean, it just gives you an example. So if you're looking at something that's similar, you can sort of look back at this and go, okay, what the heck do we have to do here, right? Okay, what are all the steps? Okay, so you might want to write this as like that. Yeah, sure. I missed this, but okay. Okay, so the outer function is I am squaring something, right? So the chain rule says, well, we take 2 times, right? So it's 2 times whatever's in here. Okay, so we just write that out, right? So what's in there? Well, we got a sine of e to the sine squared t, right? So it's 2 times that. That's the outer function, right? It's something being squared. Times the derivative of the inner function. So now we need the, so actually let's write that down. D by dt, and the inner function is sine sine e to the sine squared t. Okay, so there's your derivative of your outer function times the derivative of the inner function. I'm just enumerating this because then this we have to, again, we're using chain rule. So 2, so this first bit just sits here. It's along for the ride, right? And now we want to take the derivative of sine of something. Well, the derivative of sine of something is cos of something, right? So it's the cosine of what's in here. So times, so cosine of whatever happens to be there, right? E to the sine squared t. Times the derivative of, so again, let's be explicit here. Times the derivative of the inner function, which is e to the sine squared t. Okay, so since we're doing at least 3 applications of the chain rule, I'm just going to be very explicit about each one, all right, as opposed to just kind of writing it all out in one line, where it becomes, well, like what, where'd this term come from? Well, that's the derivative of this. Where'd this, so this, I would need the derivative of this, which starts out as this, times the derivative of that. Okay, so let's just write down our preliminary stuff. 2 sine e times the cosine and now let's do the derivative of e to the sine squared t. Okay, when you're doing the derivative of e to the anything, it just starts out as e to the anything, right? So it becomes e to the sine squared t times, and this time I'm not going to write out d by dt, but now we're just going to take the derivative of sine squared t. Okay, and we've done that before. So sine squared would be 2 sine t, and then cos t. So there's about 5 applications of the chain rule in there, I think. I lost count, but that was 3. There's 4. I think there's 5. There's at least 5. And we just got to put it all together, right? So 2 times 2 is 4. And we got this, so we've got sine, actually I don't need a bracket on the front of that now, do I? So sine e to the sine squared t times cos e to the sine squared t times e to the sine squared t times sine t cos t. Okay, so at least 5 applications of the chain rule later. There you are, right? Okay, so you just keep going down the line, right? And then, if you want to, if it makes you comfortable, then just enumerate it, right? Just say, okay, I'm going to do the derivative of the outer function times the derivative of the inner function. I'm going to do the outer function here times the derivative of the inner function. And this one, we could have written down d by dt of sine squared t. And then done it. Okay, but at some point we just say we already know what sine squared t. Okay. Last one, a little implicit differentiation, because hey, why not? Right? It's good to practice. So e to the x over y equals x minus y, right? We cannot explicitly state that in terms of x. Sorry, or in terms of y. But we can't do it explicitly. We can't write it as y equals, right? Not and just have a single y. You could write y equals x minus e to the x over y, but you can't undo that. So. Okay, so we take the derivative with respect to x of both sides, right? So how much detail do we want? Well, let's go, it's e to the x over y, because the derivative of e to the anything is just e to the anything, right? Or e to the something. Let me clean that up. Times the derivative with respect to x of x over y equals 1 minus y prime. Right, so I'm just doing the derivative with respect to x of each of the terms, right? And the right side easy, right? It's just 1 minus y prime. And now we're going to have to use the quotient rule here, right? We have a quotient, x, y. So I guess we could write it as, I'm going to use it as a quotient. Okay, so what's that derivative? Well, it's y times the derivative of x minus x times the derivative of y over y squared. So now we need to isolate the y prime, z, and get them together on one side and factor them out and divide by whatever it is. And so to do that, we're going to have to multiply this into here. And to do that, we're going to have to split this up. Okay, so let's split this up. So e to the x over y. So we'll get 1 over y minus xy prime over y squared. Okay, so what I did was take y over y squared and simplify that to be 1 over y minus xy prime over y squared. Okay, so that's how that came into being, that next line, right? I took it as y over y squared minus x y prime over y squared and simplified the y over y squared to be 1 over 1. Okay? So if you're looking at it, how did that become 1 over y? Okay, now we're going to multiply this out. So it's going to be e to the x over y, that's this times this, minus, oh, do I want to lead with the x or the e to the x? So let's lead with the x. So x, e to the x over y prime over y squared. Okay, so we've expanded the left-hand side and done minor simplification to it. And I'm going to extend the page. I'll throw that back up. So I'm going to move this minus y prime over here. And I'm going to move this over there. Okay? So I'm going to add y prime to both sides. So y prime minus x e to the x over y prime over y squared. Okay? So I added y prime to both sides. Equals, and now I'm going to subtract this term, 1 minus e to the x over y over y. Okay, so basically interchange two pieces of the puzzle, right? I took the minus y prime from the right-hand side, moved it to the left side where it became positive y prime. I took the e to the x over y from the left-hand side, subtracted it from both sides, and this is what I've got. I'm now going to factor a y prime out of the left-hand side. Okay, so all implicit differentiation really works that way, right? Is we do the implicit differentiation, we get our y, we often have to expand something. We then collect our y primes on one side, numbers are not non-y primes on the other side. Okay, I am going to write this in. Okay? So I'm going to get a common denominator here. So when I factor the y prime out, I'm going to get y squared minus x e to the x over y squared. Okay, so I took the y prime that was by itself and wrote it as y squared y prime over y squared to give me a common denominator, allowing me then to say y squared minus this expression, right, and take the y prime, equals, well, let's do the same thing over here. 1 minus, sorry, so instead of 1, we'll go y minus e to the x over y and put the whole thing over y, right? So we'll take the 1, but we'll do it as y over y and get y minus e to the x over y over y. Now, let me see if I can copy paste that onto another page so that I don't do really huge. Whoops. Hang on, I want to select. Okay. And so supposed to y minus, let's clean that up. So instead of writing divided by, are you okay if I just multiply by the reciprocal? Because otherwise it's just, going to be this over this over this over this. So let's shortcut that. Okay, and then what do we get? This y can take this y squared just down to a y. So we get y times y minus e to the x over y over y squared minus x e to the x over y.
How can the one turn into a y on the right side of there? So like y minus e.
Yeah, so I could get a common denominator. So if I want to add these two together,
So it becomes y over y, so then y.
so there's the steps, right? So the one I write is y over y. Now I have a common denominator of y, and then I write this. Okay, I just didn't sort of do that explicitly there, right? So there's your final answer. Y prime equals. Okay. And really, how could it get worse than that? I mean, like there's a lot.
Where's the y in the front?
That's, so this y took out the y squared, leaving a y, so it's y times this. So I just wrote it that way as a kind of factored form. Okay, we cannot cancel these guys because that's adding or subtracting. It's not a factor of the denominator. So there you go. I've done it all, right? We e to the x, we defined the derivative of e to the x, and we practiced it with products and quotients and chain rule 5 times in one question and some trig. So tomorrow it's what? Logarithmic differentiation, and then no. Tomorrow it's something, and then it's logarithmic differentiation, which will allow you to do question 7. Then on Thursday we start in on the new thing, which is extreme values and curve sketching. We continue that Friday. Monday's a test. Okay, so you got a weekend to kind of go through, and we just take it from there, right?